Seismic data offers an opportunity to provide a detailed look at the geological structure beneath the Earth's surface. With the aid of a subsurface seismic image, prospective hydrocarbon accumulations are selected and drilled by exploration wells. Modern seismic exploration methods provide a more detailed image of the subsurface than ever before, and the possibility of discovering oil and gas accumulations which had not been identified in the past. There are, however, two main types of seismic surveying method which utilize towed seismic streamers to acquire data. These are two-dimensional or 2D and three-dimensional or 3D. A typical modern 3D marine seismic operation includes acoustic source arrays and a number of receiver arrays. A source array consists of a number of individual acoustic source elements. A receiver array is made up of many hydrophone elements encased in a plastic tube-like skin. Both source and receiver arrays are deployed from and towed behind the seismic vessel. The source is activated, releasing an energy wave downward through the water column and subsurface of the Earth. Energy is then reflected back as a result of acoustic differences between various sediment formations and then travels back up the receiver array, where information or data is then digitally recorded on board the survey vessel. In its simplest form, the seismic image provides a picture of the subsurface in two-way time rather than depth. The image can then be converted to depth after the application of a suitable seismic processing sequence. Traditionally, due to the bandwidth of the recorded seismic data, energy emitted from seismic sources above approximately 120 Hz was not considered. The desirable characteristics of a seismic source are repulsive energy with a short time duration and a good frequency response within the traditional seismic bandwidth between 5 and 120 Hz. Many different marine seismic sources have been used in the past, such as explosives, sparkers, shockers, water and air guns. The air gun has become the predominant source element used in modern seismic operations today.
One of the benefits for seismic data is that it's sensitive to reservoir fluids. By measuring the reservoir at different time intervals, we can determine how the fluids have moved.
The real problem with 4D acquisition and processing is that the changes in the reservoir have a very small effect on the seismic.
When you're trying to bring out signal that's only 1 or 2% above the background noise, you need the best acquisition system available, and this is QMarine, QLand, and QCbed.
When you're working with such high quality data, it becomes obvious very quickly when your processing algorithms are not sufficiently rigorous. Western GECO has implemented a number of algorithms to remove the effects of survey instability from the data, and those algorithms attempt to estimate the instability directly from the data itself rather than using survey matching techniques. We have effects such as noise from nearby platforms and shipping. We have tidal variations and water velocity variations which cause changes in the seismic which are not repeated from one survey to the next. What we're looking at here is volume rendered 4D difference data produced at different stages through our seismic processing flow. At the start of the processing, we see a lot of residual energy, but when we move to the next stage, removing multiples, removing noise, and normalizing the wavelets, we start to see more clearly the problems that exist with this data. And in the next stage, we've addressed some of these problems. We've removed amplitude variability, we've removed timing variability. The next stage is regularization, which dramatically improves the quality of the data. And the final stage is migration and final processing. And here we can see clearly the 4D signal at the reservoir. We can see energy related to substance within the reservoir, above the reservoir. And look at this, we can see individual well tracks radiating out from the platform. We're able to pull out astonishing levels of detail.
Traditionally, we have been looking at time-lapse amplitude changes, and recently we have discovered that we also really have to look at timing changes. If you produce a reservoir and you have a soft reservoir, what happens is that the reservoir compacts and the overburden will react by stretching. And reservoir compaction causes a lot of geomechanical issues that can become very costly for an operator. For example, as the reservoir compacts, wells will start to buckle. We can lose them. Now, with proper pressure maintenance schemes, we can alleviate the problems of wellbore failure. But we need to have a means of monitoring compaction. Time-lapse seismic data is one of these means. Seismic geomechanics is going to be huge, and we at Western Chico are very excited about that.
There's no doubt that with the cost and risk in the deep water environment, that 4D seismic will play a huge role in the future. And it will be a necessity if we're going to make the most out of the world's resources.